hopefully you're okay with kind of the introduction we had last time to exponential function applications, using them to solve some problems. And the comparison to linear functions. Linear functions having a constant slope the whole way. Whereas exponential functions, the slope, if you think about the slope at any given point in the curve, it gets steeper and steeper. So the rate that a function is changing at is getting, higher and higher as you go along here, if it's an exponential growth thing. If you take calculus, a lot of what calculus is about is looking at slopes of curves like that and how they change. We kind of got down to what I would call the basic application type of questions, and we looked at a growth and a decay example. And the basic equation we were using, which we could probably put in this nice box here, when we had the population growth one, can't even remember what it was now, something growing at 5% or 3% or 5%. When we had the thing that was growing at 5%, we had 1500 times 1.05 to the power of x. You can use whatever letters you want. I mean, here I'm just using x for time and y is the value after a certain amount of time. For the decay one, we had the amount of students was, what did it start at? 1200 or something? 1250? 1250, and it was declining, right? So we ended up with 0.97 here to the power of x. If you have, no, you're ahead of yourself there. You're thinking of the next one, which is good that you see that. The first number here is the initial amount, right? Whatever you start with, whether it's people or it's dollars or whatever, this is the initial value. And the other thing here is the rate of growth or decay, depending on what it is. If the rate's given as a percentage, the way we model it is we're going to this is either 100% minus the rate, right? If it's going down at 3%, or it's going to be, this one is 100% plus 5%, right? Going up or down, whether it's decay or growth, right? This one is growth, this one is decay. In general, then, what you have is you have something that looks like this. Some kind of initial value called A, or whatever letter you want to use, times R. I'm just going to use an R. We could say it's 100% plus or minus some kind of rate to the X here. Don't get hung up on what letters we're using here, because if it's a specific application, if somebody's looking at population, they might say the population after a certain amount of time is the initial population. If you're a physics type of person, you probably have seen things like this, P0, population at the beginning, initial population, times R to the power of, they might be using T for time. It's exactly the same setup. It's some kind of initial value times a rate to the power of, usually time, but I guess it could be something else, whatever those variables happen to be. Okay, if you want to make a couple notes as to what that is, right? This is initial value, and the other thing is the rate. This is the rate. Okay, the rate's the hardest thing to come up with, right? Especially in the decay example where you're losing a certain percentage. And then, of course, the other things are what we expect them to be, right? This is the final value. And then this is time or something else. But usually it's time, right? We rate things as a function of time in a lot of situations. So we're going to apply that. This is our, we'll call this basic exponential growth or decay. So if that's basic, we're going to make it more complex right now. Some of you started looking at this question last time, and it's good if you did, because then I think you can get more out of us looking at it together right now. I'm not sure if you understand the situation or not, but you have this population of bacteria. They reproduce by binary fission. They just, one splits into two, right? Okay, after a specific time, a single one splits into two. If you start with 850, and typically those bacteria divide every 5 hours, we're going to think about what's happening here. So if you filled out the table, I think a lot of you had some success filling out the table. All we know is here, after 5 hours, we're going to have, how much are we going to have here? 1,700. Then the next time they're all divided is 10 hours, and what are we going to have? If they divide again, you're going to have, what's happening to this number every 5 hours? It is doubling, right? This is times 2. And you can continue that on there, right? 6,800 and so on. If we're going to set up an equation for this, writing a model function for this, it's going to be mostly the same, but let's think about how we get each of these numbers. This 1,700 here, this is like 850 times 2, right? And then this is like 850 times 2 squared, right? You've times it by 2 twice. This one's like 850 times 2 to the third. There's been 3. By then there's been 3 times you've doubled it, right? Times 2, times 2, times 2. If we write a model function, what's the problem if we do this? If we say y equals 850 times, what would the rate be here? What's happening each time? It's 2, yeah, it's doubling. That's a lot higher than growing at 5%. If it was 5% growth, we'd put in 1.05. What kind of percentage is doubling? If you had to express it as a percentage, sorry, I need something out of here. The good old Pringles can again. This Pringles can has 25% extra on top. If it was double, right? If it said now twice as much, what percentage could it also say instead of twice as much? Well, if this is 25% more, because it's 25% of the red, if the yellow was as big as the red, because that's what doubling is, what percentage would it say? It would say now 100% more, right? Because the yellow is the same as the red. Doubling here, this is like the original 100% plus the new 100%. I don't know if that helps make the connection, because I think some people find there's a disconnect between, well, if it's a percentage, they think of it differently than doubling. Doubling is just like a 100% gain, right? You're gaining 100%. So it's 2. It's like 200%, 100% plus 100%. What's the problem, though, if I just put an x up here? It's not multiplying every 1 hour here. It's after 5 hours, you want it to have multiplied by 2 once. If I do it this way and just put an x there, after 5 hours, it would be 850 times 2 to the 5. We don't want it to be multiplied 5 times. We want it to be multiplied once. What you can do is you can divide by, after 5 hours, you want it to have multiplied once. After 10 hours, you want it to have multiplied twice. The exponent you can compensate by dividing by 5, dividing by the period of what's happening there. If you put divided by 5 in the exponent, and it gets really complicated, well, for me with the sloppy handwriting, but that's the exponent, right? So that can be your model function. We're going to divide by the period. The period here is 5 hours in the exponent, and then it's going to work. Can you go through and use that model to try and solve this? calculate how many bacteria there are after 24 hours, and then try and solve this, okay? There's not much difference other than you're going to compensate in the exponent there.